Okay, we're going to get started now. Our first speaker is Björn Lütjens, who is a PhD student at MIT, advised by David Newman. His research focuses on agricultural robotics, safe and interpretable reinforcement learning, and AI for mitigating climate change in South America. He graduated with a master's in aeronautics and astronautics from MIT, and he presented his work on machine learning-based estimation of forest carbon stocks to increase transparency of forest preservation efforts at the Climate Change AI workshop at NeurIPS 2019. Take it away. You should be able to share your screen. Let us know if you have any issues with that.
Hey everybody, thanks for the great introduction, David. So my name is Björn, and I'm presenting you the update on machine learning-based estimation of aboveground forest carbon. And this is joint work with a whole lot of people, and I specifically want to point out Simona Santamaria and David Dow, who were presenting a proposal paper here, also at the iClear workshop, Lucas and Katarina, who I wrote the NeurIPS paper with, as a Sang professor of David and David Newman, my own professor. Now this is a picture of a rainforest, and specifically of a rainforest project that I was visiting 2 years ago, when I was having that big question: how can I use AI for mitigating climate change? And 2 years ago, I flew into the rainforest and I met a bunch of people. One of them was Sandro, and he said, "Well, come with me into the rainforest and explore the problem at hand." So I talked with him a lot, and one thing was flying a drone over his rainforest to see what we can do with the data we get. Now, this embeds in a bigger picture. Deforestation and forest degradation are a massive problem. They account for 15% of all global greenhouse gas emissions from 2007 and 2016. So if it were a country, it would be the third largest emitter in the world. There's some uncertainty in the statistics, but it is a big problem. Now, I think ever since 1980 or even earlier, international stakeholders have realized that this is a big problem. So for example, United Nations REDD is a great program that is paying landowners for forest conservation, thus financially incentivizing them to conserve more forests. However, to receive that money as a landowner, you have to verify that you're conserving. The problem with that verification right now is that you have pretty much two options to do it. The first one is you go by foot. Basically, you send a team of experts into the middle of the rainforest. You walk through the rainforest and you count the number of trees you see. You measure the diameter, write down the species and the height. However, this picture I took in the rainforest of Sandro, and now you can imagine how difficult it is to count every single tree you see. And that becomes quickly intractable, which makes that process very expensive. It costs, I've heard numbers of about $300 per hectare. It's also hard to scale because you need those team of experts. You will also only be able to sample specific locations, missing out on important regions, potentially missing a rare species, and in some cases it's even corruptible. So on the other side, we have verification via satellite imagery, which is great, but the resolution of public satellite imagery is currently at around 30 meters for Landsat, sometimes 10 meters. The new private satellites are currently too expensive to be used on a large scale. And with a 30 or 10 meter resolutions, you are going to have a very hard time detecting things like selective logging or roads that indicate deforestation, maybe even harder or basically impossible detecting the species. So there's currently no affordable and accurate solution to monitor small-scale reforestation or forest preservation projects. And that, I think, is a big problem. So people are proposing a drone-based evaluation system. And that was basically the idea of our NeurIPS proposal paper. We were not the first one to propose this. It was already idea around, but framed in an ML way, we were the first. So the idea here is there's a landowner. He then pays somebody, for example, a videographer that has a drone for grabbing videos of weddings. Surprisingly, I heard somebody always knows somebody who has a drone, even in the rainforest. And the drone is then being flown over the rainforest of that landowner, and you get a high-resolution imagery that you then report to an online platform. The online platform runs an automated valuation algorithm to evaluate the forest ecosystem service. And one of these ecosystem services is the forest carbon that they are sequestering for the pollutions that other countries are, or their own country are emitting. Then international stakeholders, like for example, the United Nations or Google, Microsoft, Amazon, that have amazing CO2 offsetting programs, are paying these landowners in what is called payments for ecosystem services, thus incentivizing them to keep ongoing this conservation effort. Now, this is an ICLEAR conference, so I'm going to specifically talk about this automated valuation of forest ecosystem services. And the approach basically works like this. You have a team of drone pilots, or one drone pilot, for example, here, National Institute of Geographics, Peru, that I was in the rainforest with, take a low-cost drone, for example, a DJI Phenom Pro 4, ideally with a multispectral camera, fly it over the forest and grab these patches of aerial imagery. We then derive two approaches. The first one is estimating the tree height, from stereogrammetry, taking multiple pictures, and then doing like a stereo vision approach to estimate the canopy height. And then in the parallel stage, doing a tree species classification and a segmentation. And when I say tree species classification, that's somewhat of like the holy grail. It's very difficult to do tree species classification from RGB or multispectral imagery. So I think first steps are probably the quantification of biodiversity. In other words, counting how many trees, how many species we see in one image, or doing something like a family classification, just like going on the level of classifying if it's a pine, oak, or something like that. Well, if you have this, you can then use what's called allometric equation. I'm not a forestry expert, but basically the idea is if you have the height and the species, you can tell how much biomass the forest contains, and then you divide the biomass by 2 and you pretty much get the carbon stored. The idea of why such an algorithm could work is if you look at is to exploit the difference per species in the per pixel spectrum and the structure of the image. So on the left, we can see the hyperspectral bands on the x-axis, the reflectance on the y-axis. Hyperspectral band here means there's 360 bands, which would be the equivalent of being able to see in 360 colors. And each spectrum here is a different tree. And the idea of such an algorithm would be to exploit the difference of the spectra per tree. On the right side, we can see additionally, if we leverage something like a convolutional neural network, we could exploit the structure differences per species. So maybe the left image here might look like a coniferous forest, and the right one like an evergreen forest. So to start with that, the logical first step was to gather public tree species data, to train something like a fast line, like a faster RCNN for multi-object classification from a multispectral image. If I say multispectral image, I mean an image that has 5 channels, being blue, green, red, and 2 near infrared channels taken out of this hyperspectral image. But if we go with our rule of thumb, we need approximately 1,000 tree instances per species, per class. And that's a lot of data requirements that we have here. So we started our best ever since the NeurIPS paper to collect this data. And there's been amazing people all around the world, especially, for example, University of Sao Paulo. They shared with us a data set that contains 250 segmented trees of their of their campus, and they're planning to collect 1,000 sites more after Corona is over, obviously. And then I want to point out ID3's data set. If anybody wants to tackle this task from a machine learning perspective, this is probably the best point to start. They have recently published this challenge that goes along with 731 trees, RGB, hyperspectral imagery, and LiDAR. And ETH Zurich and Waldlabor, specifically Sebastiano Ruska from Roland Siebert's team, thanks to him, they are planning to collect a data set of one more site. However, still the point being that I think I count 4,000 trees in total for something like 100 species. So we are way not near the requirement of data that these convolutional neural networks have. So there's insufficient public tree species data out there, and I think that's a big barrier towards leveraging this potential that we have with these machine learning methods. So the question here being, can we act together to collect and fuse this massive data set on tree species classification? And this would not only be useful for forest carbon quantification, but also to evaluate other things about the ecosystem service. Like, for example, quantifying the biodiversity that we have in our world's forests. Switching gears a little bit. And if you have a forest or access to a drone or know somebody who works in forestry, please don't hesitate to reach out and we can discuss more data requirements. I would be very happy to talk with you. And if such a data set would exist, it could also bring interesting machine learning challenges. For example, transfer and few-shed learning could be evaluated on the classification of rare species or the classification of data-scarce regions, like, for example, an island. It could also be used for fine-grained visual classification or for sensor fusion tests. So there's my email. Please don't hesitate to reach out. Switching gears a little bit, we were thinking, thanks to the NeurIPS conference, I found some collaborators, David Dow and Simona Santa Maria, that I started working with ever since that NeurIPS workshop. And we were thinking about, if such an automated forest valuation system exists, it can open up the possibility of the landowner reporting untruthful imagery, because we're actually financially incentivizing them to do so. So we were thinking about, what are these attack vectors that the landowner could exploit here. So if we look at the ground truth image, which is on the left, we could think of something like, one could report the wrong time, for example, before the deforestation occurred. One could report imagery just from a neighbor, or one could report a photoshopped image. So we wrote this proposal paper for iClear. Can we identify, which answers the question, can we identify the untruthfully reported imagery by matching it with public low resolution imagery? And I think that's a standard image matching problem. And we were thinking about, can we answer that with metric learning? This idea has just won Best Proposal Award. So that was very unexpected, very, 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 very cool. And I encourage everybody to check it out or look at the presentation in more detail by Simona Santa Maria. So to conclude, machine learning and drones might help to get us towards being able to have a cheap and affordable verification of forest conservation projects. However, that might open up the possibility of untruthfully reported imagery, which might be identifiable with metric learning. The next steps is to train and evaluate as the species classification and true branch on more data. In the meantime, leverage new deep learning techniques that require little data. And really the main message here is, can we work together to collect and fuse this massive data set for tree species classification. And big thanks to everybody who has been on this, CCAI organizers, academic collaborators. There's a bunch of MIT students being involved in writing some classifiers, and some nonprofits, NGOs, the government was working on this, the mentors. And I think the biggest thanks goes out to Sandro Pimentel, who we can see on the top right, who was the one inviting me to go 5 days with him in the rainforest, spend the days with his family. And I like this picture because it shows that even though we study machine learning and math all day long, they know a lot of things. So he was there and explaining me how to control this drone in this case. So something to keep in mind. And please don't hesitate to reach out.
Awesome. Thank you so much for that wonderful presentation. We already have a few audience questions. We only have a couple minutes. But if you have more questions, please put them in the chat and we'll try to get to them. Some very quick questions. Is semantic segmentation necessary, or is crown diameter sufficient?
So there has been some papers that show that you can get very far by just having the height. So if you were to have, so if you want to go with the...
Sorry, that was, and crown diameter as well.
Yeah.
The figure of crown diameter as well as height, presumably.
Yeah, so I think there's also some relation in between crown diameter and height, but I think it really depends on the region, and it also depends on the kind of forest. Like, for example, if you have a bamboo forest, then versus an eucalyptus, then you really want to go with a species because the density is so different. But I need to explore more in this forestry because these are like kind of forestry questions.
How many bands did you use for tree detection?
So we're currently working with the full spectrum and seeing how far we can get with that. Mm-hmm. And then we want to like take bands away and see how much it degrades the quality if in the end we would just be left with a multispectral with 4 bands.
A final question from the audience. Is ForestBENCH already available?
No, I wish.
Okay.
But the best data to start with is ID trees. And we wrote a bunch of pre-processing algorithms to start with that data set. So if you want to get started on this, please, I encourage, reach out again. I can share those pre-processing steps. So take over some work and get you started faster.
Uh-huh. I'd also be interested in the generalization between regions, because in the Amazon, there are about 750 tree species per hectare. And learning from US species is probably not going to get you very far. Also, there are just so many more. It's very fine-grained classification. Are you looking at more coarsifications of that classification task? So identifying to group of trees rather than exact tree species?
Yeah, I think that's a great idea. Like the first step might be just counting how many species we have per image, and then going something like the group classification, like just classifying the family, like is it a pine, oak, whatever. And then the species would be like the ultimate, big target.
Got it. Fantastic. Well, in the interest of time, we're going to have to move on to our next speaker. But perhaps Björn can stick around for a couple of minutes to answer questions in the chat. Thank you so much again for presenting.
Thanks for the invite.
We're going to move on to our next speakers from Agricola Moderna. That will be Benjamin Franchetti and Duccio Piovani. So Benjamin is the Director of Technology of Agricola Moderna, a vertical farming company based in Milano, which is growing food for a better future. Sorry, one moment. He graduated from engineering from Imperial College London, and he presented his work on deep learning in vertical farming under artificial lighting at the Climate Change AI workshop at AMLD 2020. Duccio Piovani is the head of data science of Agricola Moderna. There he uses machine learning to improve the way we grow plants in vertical farms. He received his PhD in applied mathematics from Imperial College London. Please take it away. Thank you so much for joining us. You're going to have to...
Hello.
Okay, we can hear you fine.
but I'm trying to get the present. I cannot find the presentation.
Try maybe a different. We can see it.
Oh, you can see the slides.
They're not full screen, but we can see them.
All right. Sorry. Are they full screen now?
All good. Yes, they are.
Great. Okay, perfect. Yeah, so thanks a lot for the introduction. I want to stress also that this work has been done in collaboration with La Sapienza University. Yeah, so we are currently sitting in our facility here at Agricola Moderna. We've been one of the lucky few here in Milan which have been able to work in this period. The main reason is that we are producing food, and so they're allowing us to stay open. Very briefly, yeah, as mentioned, we are a vertical farming company based in Milan. We are now operating a 1,500 meters squared facility, and we are producing primarily leafy greens that we are selling to Carrefour supermarkets in the area. At the moment, we are producing about 2 tons of salad every month. And we're in the process of building a much larger facility in the area. So just a brief history. And yeah, my goal in this presentation is to convince you that vertical farming can have a positive effect on agriculture. And then Lütjens is going to speak more about how we're using AI in vertical farming applications. So this slide, yeah, you've seen a bit of it in the last couple of days, but yeah, essentially agriculture is not sustainable as we have it today. So why? First of all, one of the reasons is a lot of water is used in agriculture. So around 70% of fresh water used today is used for agricultural purposes, and the remaining 30% is mostly industry, and just very small amount is for human use, personal use. The other thing is, of course, agricultural processes produce a lot of greenhouse gases. About 25% of all greenhouse gases produced come from agricultural processes. And also, agriculture uses a lot of land. As the population is rising, and we expect to reach around 10 billion people by 2050, we expect to need more land for agricultural purposes of the size of Brazil. But the main problem why agricultural processes are not sustainable today is because humans have got used to a kind of food supply system which is very unsustainable. First of all, we want food production year-round, so we want the avocados all year round, and food has to travel very long distances to reach our plates. On average, food travels 1,500 kilometers. And in this process, a lot of food is wasted. Around 30% of food goes to waste before it reaches our plate. And in addition to that, the food that finally reaches our plate is often unhealthy. It's not fresh, lacks nutrients, and is covered with pesticides. So not only we are hurting the planet, we are also producing unhealthy food which are not great for us. For this reason, we have decided, we think that vertical farming should be part of the solution. So a bit about the advantages of vertical farming. I'm not sure if this, okay. So first of all, vertical farming can be better for the planet. So in a vertical farming system, you produce around you consume around 95% less water because you recycle the water and the nutrients inside. So you don't get the problem of polluting the land with nutrients. Also, in our vertical farming processes, we manage to be around 100 times more productive than in traditional agriculture. So that essentially means 99% less land is needed. In addition to that, we can produce food close to the point of consumption. So of course, that means fewer kilometers to reach our plates, but also less food waste because we can produce based on people's need. However, although for vertical farming has very high capital intensive costs, so for this kind of technology to be economically feasible, we really need to work on our operating expenditures. Based on the know-how we have developed over the last year or so running our pilot facility here, we've came to really understand what are the main things we need to work on. One of the things, of course, that where we can bring a lot of advantages on artificial intelligence, but wanted to briefly mention another few things. For example, fully automation. This is very important in vertical farming. We need to industrialize the farming system. Another important thing is that we need to produce electricity on site. And we need to be close to the logistics centers. A lot of people say you need to be close to the cities. That's true, but most importantly, you need to be close to the point where the food is distributed to the supermarkets. So another advantage of vertical farming is that we're discussing before, a lot of the food that reaches our plate today is not healthy, lacks vital nutrients, is full of pesticides. In this way, instead, we are able to produce a premium product, which is actually accessible for everybody. So we don't need to anymore have to decide between quantity or quality. In fact, we can produce high quantity of produce with very high quality too. And essentially what this means is that we are able to produce a produce which is healthier, fresher, and tastier. But, you know, of course, it's not all good news. This is probably what a lot of people are wondering. Is this sustainable? So we've seen that there's a lot of positive aspects, less water consumption, less land use, less kilometers, the produce is fresher, etc., etc. But in fact, we're producing indoor. We're not taking advantage of the solar energy. So indoor farming is extremely energy intensive. For example, in the 10,000 meter squared facility we're developing, which we are going to consume on average around 40 megawatts a day of electricity. So essentially, we believe and that for vertical farming to work, to be environmentally feasible, it has to use renewable energy. And this brings me to my last slide, which actually it's taken from the slide I've seen on Sunday by John Platt, and I was really happy to see it, is that I think we need to start to think about electrifying agriculture. We've been seeing, why don't we electrify heat? Even before we were discussing about electric vehicles are really only sustainable and renewable if we use renewable energy to run them. And in a way, I see the same thing for agriculture. It's less difficult, increasingly it's going to be less difficult to produce renewable energy for the grid. So we ideally going to live in a world where we're going to have a lot of renewable electricity. And with this electricity, we can power our electric vehicles, our heating, and why not potentially also some vertical farms for producing a lot of our fruit and vegetables. On this note, I'll leave now to probably what you guys are even more interested on, which is the AI part.
Okay, so thank you, Ben. How do I switch slides here? Okay, yes.
Yeah.
Great. Okay, so yes, thank you. So as Ben just mentioned, the vertical farm brings with it many good things, and unfortunately there are several major open problems to it. One of them is, of course, energy consumption. Another may be the fact that not many, which is strictly related, not many types of plants are sustainable under these conditions. But one of the reasons that we are optimistic relies on the fact that we believe that this is it's perfectly suited for a quantitative and systematic approach. We've just seen in the previous very interesting presentation how hard it is outdoor to gather data. This is so we have to build expensive material on drones and make them fly under varying conditions, and transmit in some way the data from the engine, or just store it so it's heavy. I mean, there are many problems. This, of course, vertical farming happens indoor. We have absolute control on every detail of the environment. Of course, it becomes harder and harder if we scale to larger sizes, but we can control the temperature, the pressure, we can control the light, we can control the type of light, the intensity, we can control the wavelength. So this is really an ideal situation to operate for a data scientist, because you can vary the conditions as you wish. It's a stable process in the sense that once you create the same conditions, the outcome will be extremely similar. And moreover, there is this fact that you can build and install sensors relatively easily. I mean, it's not easy, but it's a lot easier than than what we've just seen. So we can control, monitor, and stock data on every little aspect of a plant's growth. So I'll go to the next slide by just going through and sketching a pipeline of work for non-invasively and in real time monitoring what's going on. So this is, we work mainly with images at the moment. We have 3 types of sensors, which is RGB cameras, of course, depth maps, so depth sensors that tell you the distance between the camera and the plants. And we've just started to work with hyperspectral imaging, which is, of course, extremely promising. So the sensor can communicate only a few things: when the data has been taken, who he is, so where he is in the farm, and what he's actually telling you. So the measurement, in this case, the image. This information is useless if it's not put into a context. So database management is very important at the same time, and where all the experimental conditions are kept, what the plant is, what the light is, and so on and so forth. There's another, so the segmentation step is where the deep learning and the AI, under AI, there's a lot of techniques from a linear regression to recurrent neural networks. And so where we divide the plant from the background, we phenotype it through algorithms, and then finally we aggregate and analyze the results and compare different conditions. So let's take a quick look at every step. So we are building a proprietary database at Agricola Moderna, and taking into account many different types of growing conditions, seeds, species, and results, of course. This is done with the state-of-the-art technologies, and we've built with our software developer an app to interface with the database so that the agronomists, which don't have necessarily a numerical background, can interact. I think this is one of our major good things. And moreover, we are labeling a vast amount of data. So this is, of course, this is our knowledge database. And we know everything about the image I'm showing. So we outsource this to an external company. Then segmentation. So many of you know what I'm speaking about. This is where the deep learning takes place. So we have to segment the RGB, and we've started from an off-the-shelf Mascar CNN. This is extremely easy to use because it's all done for us. It's pre-trained and amazing. So all we have to do is take it and apply it, and it gives decent results. There is a step of overcrowding because the number of instances is very high. So we're working on improving the architecture and moving on. So beyond Mascar CNN, by coupling this information with a depth map and with the intrinsic parameters of the camera, we are able to reproduce a point cloud. So a point cloud is just, every pixel is given an XYZ coordinate. But if we segment and we tell them, okay, this bunch of pixels here belong to the same plant, and this bunch of pixels here belong to another plant, then we are able to separate and reconstruct the three-dimensional structure of that specific plant. That's when the phenotyping comes in, and through very standard procedure. We take these meshes, we take the point clouds and we apply a three-dimensional meshing, and then we can study the area. We can monitor the area of the leaves, the height, and then length and width, and other geometrical, more complex geometrical features. The weight, of course, is slightly more complex because we have to couple it with the measurement of the weight. So the idea is that we were trying to study, for example, what's the role of shape, how do plants compete for space and stuff like that. This brings us to our last step, which is aggregating up this bunch of data and understanding under the conditions, monitoring the process. So before we built this system, the agronomists were forced to cut the plants and invisibly destroy them and then measure all the things by hand, which took forever. Today we have cameras that do this for us. And this is very quick and very efficient. This is just a few examples, and as we can see from the figure below, we can compare different conditions. So what's going on? So for example, PAR is like the light intensity. With the blue, we've seen that this is kind of surprising because a lower intensity produced a higher weight. So this is the type of optimization I was talking about. Moreover, so what are our next steps? So we built these basic phenotypical traits for automatically measuring what's going on. Now we want to move on to going to more qualitative things, and such as measuring the amounts of chlorophyll, the pigments, the amount of stress, and other things which are available. It's available information inside the hyperspectral signature of the plant. I'd like to stress that this is really a very exciting field for a data scientist because of the relative abundance of labeled data and the absolute control we have on everything. And so I'm very happy I invite more people to get involved, definitely. And that said, I'd like to thank all the collaborators from our team. So that's we've got two data scientists from La Sapienza, so it's Malik and Mikkel, who actually did the job with Professor Pirri, and our software developer Dario, who's taking care of the database and the app, and our agronomist Chiara. Thank you very much.
Awesome. Thank you so much for that wonderful talk. So I wanted to ask a couple of, could you mute yourself while I'm speaking because I can hear an echo? Wanted to ask a couple of questions from the audience very quickly. So just to combine them, can vertical farming produce rice or wheat and other staple foods, or can it only produce vegetables and fruit profitably and economically? And then the related question is, which crops do you expect to grow economically at which inflection points? Currently, most vertical farms produce lettuce, but where could it go in the next years and what would it take to get there?
Yeah, that's a great question. So, I mean, in vertical farms, you can produce anything. The question is, what can you produce in an economical way? So at the moment, people are excluding for the foreseeable future staple crops, really. So anything which is rice or wheat or things like that. However, and it's becoming increasingly standardized for what are called leafy greens, such as salad. And now there's all of the fruity crops, which can be anything from an aubergine to a strawberry. And within that range, there is things you can do already right now, such as strawberries, and things which you can't, but people are starting to work on, like watermelons. Now, what is needed for this to become economically possible is, first of all, it's a combination of a few things. I would say the number one most important thing is energy. So really, if energy costs, if you start to self-produce energy, then already you can cut around 20%, 25% of your costs. The other critical thing where there's a lot of research is genetics. So there's a lot of research right now on developing new breeding varieties, for example, new tomatoes, which don't grow as high. They are able to stay smaller and are more appropriate for vertical farming applications. So it's really, when we got into it, people were saying this doesn't make sense for anything else than microgreens or very small plants. Already now it's expanding to more crops, and I think that this sector will, we believe it's going to be the way of growing fruits and fresh fruits and vegetables which are don't come from trees or don't have a high calorific value.
Awesome. Thank you so much again for your talk.